Hi there. Let me introduce you our app, ElderGuard. With Singapore moving towards smart nation digitalization, more elderlies are starting to embrace the use of smart mobile phones in their daily life. However, this inadvertently exposes them to malicious content through their smartphone. Adversaries are targeting elderly who tend to be less tech-savvy by sending them fraudulent text messages or URLs that they unknowingly click. This not only results in financial loss or identity theft but may also cause them to lose confidence and abandon the use of smartphones. Our main aim is to build an app that helps them to detect text messages that may be fraudulent in nature. Examples are spam messages or messages that contain malicious URLs, or phishing URLs. This app shall protect elderly from being scammed or cheated by alerting them whenever they receive a suspicious text message. This is how our overall app system design looks like. Our ElderGuard is an Android application that interacts with users and obtain messages to be classified as safe or unsafe. Flask app is hosted on Heroku platform and contains 3 pattern recognition modules for detecting spam text, phishing URL, and malicious URL. The training process starts with loading up the labeled datasets. The datasets will go through a text pre-processing process. This text pre-processing is mainly to remove some unnecessary information in the text messages. With pre-processed text messages, we split the dataset into training, validation and testing set. As models usually only take numerical inputs, we will need to convert or transform the text messages into numerical representations that are able to capture the essential features for model training. We have designed and fitted various methods of feature extraction on the training datasets. The feature maps are then fitted into various machine learning models, traditional ML models and DNN-based models, for training. We then go through the model selections and evaluation process to obtain a list of candidate models that return great performance in spam text classification. Whenever a raw text message comes into the spam text module, the serialized objects will be called in sequence and inference will be performed. As there are multiple models selected for deployment, the final prediction of ham or spam are defined by the majority vote of the model inferences. The final output of the spam text module will be a binary score of 1 or 0 to indicate if the text message is spam or ham. To train and develop the spam text classification module, we have selected and utilized the following datasets. Before proceeding to feature engineering using the dataset, we applied some common text pre-processing to the data. Notice that we have 2 types of outputs from the text pre-processing. This is because the token-based and string-based format data will be utilized in different feature engineering methods in the later steps. The methods of feature design and extraction is generally separated into 2 groups. One is for traditional ML models while the other is for DNN-based models. A total of 5 feature representation methods are experimented. In traditional ML models we utilized all 3 types of feature maps in training 6 types of models. The testing dataset is used to evaluate the performance of the model on unseen dataset. This is done to prevent information leakage from the testing dataset during the hyperparameter tuning procedure. Besides, evaluation based on unseen data is very important here as our dataset has an imbalance ratio of ham versus spam. Similarly, for DNN-based model training, we utilized both the pre-trained word embeddings as well as word embeddings trained from dataset in various DNN model architecture. We have experimented with 4 types of model architecture, namely dense classifier, CNN, LSTM and CNN LSTM. Intuitively, the dense classifier would not be very useful here as there is no feature extraction layers in the model architecture. The CNN, LSTM and CNN LSTM are among the popular DNN models that are used in classification tasks. All DNN models are constructed and experimented using the TensorFlow and Keras deep learning packages in Python. Operations and tuning are conducted to each of the DNN models experimented in order to optimize the performance. Below are some layers or modification methods that we have used in tuning the DNN models. Most of the models performed well for dataset and testing accuracies are at least 90%. Based on the testing accuracies and F1 scores, Random Forest and KNN performed the best using the manually designed features. Naive Bayes performed best when using the bow count vectorizer features. SVM performed best among all comparison when using bow TF-IDF vectorizer features. The performance of logistic regression is more average across the three types of feature maps used. Finally, the ADA boost performed the worst as compared to other models here with accuracies below 97% and F1 score below 90%. For DNN, an observation based on the results is that the models with word embeddings trained from the dataset generally performed better than models with pre-trained glove models. This is expected because the glove embeddings were trained using unsupervised learning algorithm to obtain a general vector representation of words. On the other hand, the word embeddings trained based on our dataset will be more useful for the spam text classification task as the backpropagation mechanism will steer the embeddings trained to be more catered to the nature of ham and spam text messages. We can see that the CNN and CNN-LSTM models with word embeddings training have the highest testing accuracies of more than 98% and F1 score of more than 94%. This is aligned with the literature findings where DNN-based models with word embeddings can perform slightly better traditional ML models. Here is the list of considerations that we need to consider when selecting models for deployment. Although most of models trained achieve great performance with accuracies above 90%, we need to also consider the additional points listed in here. For ML models, we have selected 3 models for deployment, namely Naive Bayes with bow count vectorizer, SVM with bow TF-IDF vectorizer and KNN with manually designed features. The selection criteria for model evaluation metrics is defined as more than 96% of testing accuracy and more than 91% of F1 score. For DNN-based models, we have selected CNN with word embedding trainings for deployment. Even though both CNN and CNN-LSTM with word embedding trainings have almost the same performance and are the best among the models trained, the CNN is selected due to the number of parameters of the CNN model is slightly lower at 359,435 as compared to CNN-LSM at 407,851. This is our pipeline flowchart for phishing URL detection module. We start by doing data pre-processing on the datasets, followed by feature extraction and splitting this data to build and train our models. Here, we make use of 5 traditional machine learning models, and conduct evaluations to finally do a selection for our phishing URL classification task. To train and develop the phishing URL classification module, we have selected and utilized the following datasets. Few features extraction methods are used in this project to find a new representation of the important features of a phishing site, including lexical features, bag of words with count vectorizer, and TF-IDF as feature representations. A total of 24 different lexical features are used to differentiate between phishing and non-phishing URLs. Table here shows the machine learning algorithm and hyperparameters used in the training. With the features described in the previous section, we used multiple machine learning algorithms to learn the models for phishing classification. The model is then tested using unseen test data to assess the model accuracy. Datasets are dividing into 2 subsets, 70% used to fit train the model and 30% not presented in training stage. Instead it is used as unseen dataset for evaluating the fit of machine learning model. Based on the performance results of model training, we selected the top performance for each of the category for model evaluation. The selection of model and input pairs is based on the testing accuracy and AUC score for each of the category pairs. With the performance criteria of at least 85% testing accuracy, 85% of F1 score, and 92% of AUC score, the team has selected these models to be deployed. Ensemble models combination approach with weighted voting based on accuracy is used to get the final prediction. This is our pipeline flowchart for malicious URL detection module. We start by doing data pre-processing on the labeled datasets, followed by lexical feature extraction and splitting this data to build and train our models. Here, we make use of multiple traditional machine learning models, and conduct evaluations to finally do a selection for our malicious URL classification task in the deployment swim lane. Since there are already numerous work in this area of research, there are quite a few publicly available datasets to work with. Datasets resources from Kaggle was mainly utilized in the model training and testing. In order to build a lightweight classification system that can produce fast prediction results, only lexical features from the URL string is extracted and analyzed. A total of 23 different lexical features will be extracted and used as feature maps to train our malicious URL classification model. During the model tuning and validation, it was discovered that the binary features extracted did not have any significant impact to any of the model performance. This is likely due to the dataset that was available to be used in this project are not sufficient enough to be useful. Hence it was decided that this binary feature will be discarded. Using the 23 lexical features as mentioned previously, the entire dataset was split into 70% for training and remaining 30% for testing. 5 different traditional machine learning models were used in this training phase. Besides the training and testing accuracy, given the class imbalance, the F1 score is also important since the false positives and false negatives are also crucial as we are predicting whether a given URL is malicious or otherwise. From the charts, the random forest, decision tree, and KNN models gave consistently higher performance compared to the rest. To simulate a real case, 10 known safe URL sites and another 10 known malicious URL sites are input into our malicious URL detection system to test our system. However, one main observation is that the KNN model did not perform well at all. Instead, ADA Boost model proved to be the next best detection model and was used to replace the KNN model. Finally, an ensemble averaging approach using simple averaging was adopted between the decision tree, ADA Boost and random forest to predict whether the input URL is malicious or not. For backend, a Flask application is deployed and hosted on Heroku. All of our 3 modules, spam text module, phishing URL module and malicious URL module are contained in this Flask application. The extracted URL and text obtained from the ElderGuard Android application will be wrapped as a query and forwarded to Flask server hosted on Heroku. For the front end, the team has developed an Android application for the end users. From the interface you see here, users can interact with the application using these functions provided by the ElderGuard. First, read last message. Second, take picture. Third, select screenshot. Fourth, extract and display text. Fifth, perform real-time prediction. Last but not least, display result as safe or unsafe. Let me show you how our read last message function works. Next, let me show you how our take pictures function works. Next, let me show you how our select screenshot function works. Our team have successfully developed a machine learning-driven application to predict the safety of a text message, explored various feature engineering methods that represent text messages or URLs, and evaluated the performance of various machine learning and deep learning neural networks for detecting malicious content. Finally, our team have selected performing algorithms taking into account careful considerations such as feature representations, size, inference speed and complexity of models, and developed an Android application with the predictive engine deployed and hosted on Heroku. Thank you for watching. Goodbye.